Hello, I would like to welcome our dear audience to our webinar today, entitled EEG Preprocessing, Setting Up Your Data for Optimal Analysis. My name is Fernando Cross. I am a scientific consultant at Brain Products, and I will be your presenter today.
Hello, everyone. A warm welcome also from my side. My name is Kidist, and I'm happy to be your today's moderator.
Hello, also from my side. My name is Michael, and I will assist Kidist with moderation today.
All right. Well, after going through these procedures, I would like now to introduce the objectives from our current session, where we would like to clarify the concept of preprocessing as the preparation of EEG for data analysis, to provide rationale for designing preprocessing pipelines under different circumstances, to show how the order of linear and nonlinear preprocessing steps can affect the analysis outcomes, and display analyzers options and usability for preprocessing. The webinar is structured as follows. We will go through an introduction where we will cover why preprocessing and the types of preprocessing, designing a preprocessing pipeline with considerations when building a pipeline, and parentheses in re-referencing and the independent component analysis step. Then we will go through the sequence of preprocessing steps when reviewing also the effects of the processing sequence, linear and nonlinear steps. And finally, we will see some adaptations for preprocessing pipelines for different EEG analysis. So let's begin. To set preprocessing in context, let us go through the process of data analysis. Preprocessing is, of course, the first steps that we do when we receive our raw data, where we start preparing the data. Afterwards is followed by data processing, for example, when we get our measures of ERP analysis, followed by result generation, where we extract measures to report for later comparison between groups or conditions, for example, getting the peak or the latency out of the ERP component. And then we will automate the processing pipeline to other data sets. Taking a closer look, of course, exporting for statistics, but taking a closer look, then we will inspect and adjust the data during the pre-processing and clean the data as well. Then for the pre-processing, taking also a closer look, we will extract our EEG measure at the subject and the group level. And this process may require some revision and fine-tuning, after which, once we are satisfied, can proceed to visualization and extraction of the results, and finally into statistics and publication. But today we are focusing on this very first step, the data preprocessing. So why preprocessing? So raw data as we receive it is often not suitable for analysis and needs to be brought into a form which is appropriate for further computations. And of course, EEG signals are quite often contaminated with non-neural signals, which can be from physiological or non-physiological artifacts. In this way, preprocessing is the intermediate process that separates the relevant neural signals from random neural activity. And it also facilitates the path to reach the final goal of data processing or analysis, which can be either analyzing an ongoing brain signal or the alteration due to external stimuli, having a reliable interpretation of an ERP component, or extracting reliable features from desired analysis domains, such as analysis at the scalp level or analysis at the source domain. But let me better show you what I mean. For example, here we have a picture from raw data. And if we took this raw data and directly went into averaging to get an ERP around stimuli, then you can see this ERP waveform has some noise into it, and it also offset away from the zero level. And well, while it's good news that we can see an ERP waveform without any preprocessing, this ERP waveform would be difficult to interpret because of the lack of preprocessing. In turn, if we first execute our preprocessing and then obtain our ERP, you may already notice some differences in the reduction of the noise and the ERP baseline being centered around 0, which will improve our interpretation and feature extraction from this ERP waveform. But let's take a closer look. So here, for example, if you look into the waveform on the right without pre-processing, well, as we've mentioned before, it's off-center, but the consequence of this is that the mapping here is not precise. The topography is altered because it's reflecting rather the offsets of different channels rather than the topographic distribution of our ERP waveform. Then we also have the high frequency noise, and this noise in turn makes it difficult to locate the peak of an ERP component, for example. On the other side, if we see into this preprocessed waveform, then first it's centered around 0, and this centering has happened for all channels, which allows us to better see the distribution of our ERP components. It's also reduced in the high frequency noise, and that allows us to do a more precise location of the peak of an ERP component. And so on, it can happen for different kinds of analysis, such as in this example with ERP, but could be also be others like frequency or, for example, connectivity analysis. Pre-processing will help us to achieve a more reliable interpretation. Then we have different types of pre-processing. So in inspecting and adjusting the data and cleaning the data, these procedures can be applied either on a supervised, unsupervised, or a semi-supervised manner, with the unsupervised being, for example, with the unsupervised being the computer realizing some processing without any user intervention and generating some outputs. Then with the supervised version will be a manual inspection done by the user. The semi-supervised being an intermediate between the two, where first the computer can execute the processing, then the outputs can be verified by the user, either to modify them or accept them or reject them. And the different pre-processing steps that can be applied, just to mention a few of them that we will later review, can be change sampling rate, using filters, rejecting artifacts, topographic interpolation, having a new reference, editing the markers, segmentation, also called epoching, baseline correction, or pooling, for example. These kind of steps can be applied either to continuous data or segmented data. Some steps are better suited for continuous data and some better for segmented data, or some other steps are applicable to both equally. For example, if we take edit markers, this can be applied either to continuous or segmented data according to what our requirements may be. Baseline correction is almost exclusively applied on segmented data, while filtering is preferably applied into continuous data. Many more pre-processing techniques exist, which we cannot cover in this webinar, but I would like nonetheless to give you some examples, such as the rectifications, which will return the magnitude of the values in positive numbers, DCD trend, which will remove a linear trend from the data, level trigger, which it will detect a threshold and set a marker when reaching that threshold, in this example, when the data crosses the 0 level, or electrocardiogram R marker detection, where the computer or analyzer will find the R peaks of the electrocardiogram and set an R marker there, which can then be used for different purposes. Add channels will allow us to introduce data from different measurements, for example, from eye tracking that we can see here, but you can find more information about this kind of transformation in our webinar channel. There are some research domains that involve special techniques due to their special characteristics. For example, the EEG fMRI combined measurement, where analyzer offers the MR correction, cardioballistic correction, and carbon wire loop regression. Or for example, TMS EEG, where analyzer offers the interpolate time range solution. When we come into designing a preprocessing pipeline, there are certain considerations that we need to keep in mind. So choosing which steps to implement and in which order is quite a relevant decision. And this decision can be informed by the knowledge of a particular processing step. For example, if this step involves linear or nonlinear operations, the effects that these operations will have on subsequent processing steps, for example. And other factors to consider are the characteristics of the data or our intended EEG analysis. Predefined pipelines can be used from previous studies, guidelines, or from lab procedures, for example, but also it is possible to adapt new pipelines according to the requirements that we may have at hand. For this, we need to keep in mind always the rationale that we are using for adjusting the different preprocessing steps. And the pipeline, once we decide for a pipeline, should be consistent for all the datasets that we have in a study. So in the following, we will build a preprocessing pipeline as an example, where the rationale for deciding at each step will be clarified. The type and the order of the steps can vary for diverse reasons, but this will be emphasized towards the end. Important to mention is that the example that we're showing here is not meant as a recommended standard to use. What we rather would like to highlight is the rationale for deciding which step at which moment to use. I would like to introduce the dataset that we are going to use for the examples. So this is a recording with 64 channels plus a bipolar EOG recorded at a sampling rate of 1000 Hertz. And the recording consists at first of a resting state with eyes closed 2 minutes and eyes open 2 minutes. And then comes the emotional picture viewing paradigm, in which we presented to the participants the emotion-inducing pictures from the Nemke affective picture system. And this consists of pictures that elicit positive, negative, or neutral emotions. But today, for the examples, we will be only focusing on the positive pictures. These pictures were presented in 4 blocks, and between each 4 blocks, there were free-paced breaks where the participants could move and relax freely. We will implement the common preprocessing steps for EEG overall, having an emphasis on the direction of obtaining ERP, but then towards the end, we will also show adjustments that can be implemented for specific EEG analysis, such as the frequency or time frequency analysis. So having introduced already the dataset, let me come to Analyzer to introduce you how we're going to work with the datasets. What we have here are 4 datasets. Dataset number 1 is twice here, so we have a copy, because we will start processing from the beginning with the original dataset, and then the copy dataset has been already pre-processed all the way until independent component analysis, because this transformation takes longer to compute. So here it has been already computed. While these other 2 datasets, we are going to use only to highlight certain properties of the transformations, or, for example, what happens when we switch the order of the transformations. So let's begin. And for that, I'm going to open our dataset, our main dataset, which we can observe over here. And first, I would like to draw your attention down here to our navigation bar. We can use here these buttons to scroll through it. but it also has different markers on it that are very useful for orientation. So at first, if you remember, there's first a resting state with eyes open and eyes closed. And here you can see the markers that were introduced to indicate when the participant had the eyes closed or open. So here, for example, we have eyes closed end. Then the next one is eyes open start. And then by the end of a period, there's eyes open end. And then repeat the procedure. You may notice then these 4 clusters of red markers. These are stimulus markers that show us when each one of the pictures were presented. And they have different codes, with S1 that we see here, meaning a positive emotion picture. And we have here other S3, S1, and so on. So this come here in 4 clusters for the 4 blocks. And in between them, you see the lack of markers. This indicates us that this was the break period where the participant was moving freely. And as such, you may already notice that at this part, the data shows many more artifacts because the participant was moving. But all right, once knowing this, in getting to know our data further, we can right-click and select Properties, where we can see our number of channels, so the 66 channels, then the sampling rate of 1000 Hertz, and other data like the number of data points and the length of the data in seconds. Something else that we can do to check all our markers is right-click. Now we come into Markers, and we can see a summary of all the markers that we have. So we have the ones eyes closed and eyes open, and the 3 markers for the emotional eliciting pictures. And we can see that we have 180 from each one of them. So to start pre-processing, the first thing I would like to do is to rename our positive picture marker from S1 to positive. This will make it easier for me to remember which is which every time, so more intuitive. And also, if I would like to share the data with someone else, they would also recognize more easily which kind of stimulus was being presented. So now that we are in the raw data active, now we can come into transformations, and we can select the option to edit markers. Here we have 3 modalities, but I'm going to use the automatic modality because it allows me to change many markers at the same time. So I'm going to next. Here I can select the marker types that I would like to modify. So the picture presentation is a stimulus marker, so I choose stimulus, and then I choose the one that I want to modify, S1. And down here I can introduce the changes that I want to make. So I want to change the description or the name from S1 into positive. And then click Add. And this means now this change is already introduced in the list. I could introduce more changes and then click Add and have them all here. But right now I'm only going to use this one. So I will click now on Finish. And if I again do a right click and come into markers, then I can see there's no longer S1, it's now called positive. All right, and then a second step that I would like to do now is to change the sampling rate, because the data, as if you remember, has been recorded at 1000 Hertz, which is very convenient. But to save disk space and also to increase the processing step of subsequent processing steps, the processing speed, then I'm going to reduce it to 500 Hertz. So I can come here into this transformation, change sampling rate, and it's showing us the current rate. And what I want to use now is 500. Which is still very well sufficient for ERP frequency and the time frequency analysis that we want to do later. So we can leave it like this. And here we have some options about interpolation, but these are only relevant if we were upsampling the data. So right now we can ignore this and just click OK. And if I want to know what change was done here in this new node, change sampling rate, then I can right click on it and go to operation infos. And here it's telling me new sampling rate 500 Hertz. Okay, I can also click or right click and rename here to remember more easily what was done, and I will introduce 500 Hertz. Okay, so here we have it, and now we can start with our data exploration. So it's always a good idea to take a look into the data to get a sense of how it is going. And overall, this is a clean data set, especially here at the beginning that the participant had the eyes closed. But here the participant already opened the eyes and we can already see some blinks. And let me show you when we come to our presentations, we see some blinks as well. And all right, let's see, because we have 64 EEG channels, so we don't see all of them here. So to see more of those channels, we can click this arrow here to go to the next page. And we can see the rest of the channels and scroll around them. And something that is normally done in the exploration, or that can be very useful as well, is if you want to map the evolution of the data. So for example, I can click and come into mapping view to generate the map. And here, for example, if I try in this state of the data to drag the cursor, I see that nothing is happening. So the values seem to be changing. However, in the map, there is no large change. So if I try also to make an area and drag it around, I can also see that there is no change in the map. And the reason for that is that from my original recording, all of these channels have an offset away from 0. And that's a result of my amplifier settings. It's not an error. It's quite normal that this happens in some recordings, depending on the amplifier settings. And the offset, we don't see it right now because Analyzer is centering the data for us for each channel. However, I can deactivate that option and come into this button here. And if I press it, then the centering function is deactivated and I no longer see the channels because the offset is so large that it's basically off the screen. So to get an idea, we can put our cursor in a channel, and then if you look, if you look on this region over here, it's going to reflect the value, and we can see here, for example, it's greater than minus 2000 microvolts, which is, of course, beyond what EEG normally reflects, and it's just the channel offset. So basically, this map is showing us the channel offset. But as I was saying, this is not a problem because this can be addressed by filtering the data. So this offset can be considered as a very slow oscillation or a very slow frequency. And when we use our filters, then we can filter those slow frequencies out and reduce the offset. So, but now to explore further, let me bring back all our channels to the center and continue my exploration. And here I see something, this channel over here, F5, which looks rather noisy. So it was probably loose, and whenever the participant moved a little bit, then this channel shows this kind of drift, which also can be considered as a slow oscillation. And we see it's not the only one, but it's certainly more severely and more consistently affected. Okay, so let's try to see if the filtering will reduce the noise in this channel, and also use filtering to reduce the channel offset. So for that, we come into data filtering and select IIR filters. Here we have our filters settings. So here we have the low cutoff for reducing the low or the slower frequencies, and I'm going to use a criterion of 0.1, which is commonly used, and a filter order of 4, which is also commonly used. For the high cutoff that will reduce the faster frequencies, I can use 40 Hertz and also an order of 4. And then on top of that, we can add a notch filter for reducing the line noise from the electric grid or other devices that may be polluting the data. Here it's set at 50 Hertz because the data was recorded in Europe. It could also be set at 60 Hertz, but right now I'm going to keep it at 50. And probably you are already noticing in this plot over here how it changes as I change the settings, and that's because it's reflecting the response of the filter to different frequencies. So if I either, for example, change some setting here, I remove the filter for the 50 Hertz noise, so this part of the spectrum is not affected, or I can add it again where we see then the filter response again. But I would also like to draw your attention to this option here, which says store data in cache file. And that means that after filtering, the outputs of the filter will be saved in the hard drive. And this will help us speed up the display of the filter and also the subsequent pre-processing that we will do. So if we do not choose it, then Analyzer will resort to on-demand processing. So every time the filter node is called, the filters will be recalculated, which will slow down subsequent processes. So I can now choose to use it, and I will go into OK, which we see now it is creating the filter cache, writing the outputs into the disk, for which right now we have to wait a little, especially since this data set is a little long. However, the advantage of waiting now is that we will not have to wait later, and the subsequent pre-processing will also be faster. So we're almost there. And yeah, now we have our filter outputs. And one of the first things that we can do is check that the offset has been largely reduced. So I'm going to deactivate the filtering option. And now you can see that all our channels remain in there. And that's because the offsets have been reduced after filtering. And that allows me also to generate the mapping view. And now I can really, for example, track the evolution of the data. So if you find an artifact and want to check how it's affecting the scalp, for example, here, this blink artifact, I can bring the cursor here, and now I can really confirm that this blink has the typical distribution of a blink on the scalp. But all right, so let's see if our noisy channel has been fixed by this filtering. So for that, now I would like to use this option, which increases the channels on the display. And we locate our channel F5 over here. And we see that it's still showing a considerable amount of noise despite the filter. The others improved, but this one is definitely still severely affected. So before following with other processes, I would like to do the interpolation of this channel so that it doesn't interfere with other processes that we are going to do. So for that, from our filters node, I will come here into topographic interpolation. And in this dialog that opens, here on top, we have different options for interpolation. And normally the standard options are doing quite a good job, so I'm not going to modify them. But here I would like to call your attention to this one, keep all channels, which means that after interpolation, we can keep all the other channels that were not interpolated in the display as well. Here we can type in our channel name, or another option is to select it from a map. And for example, I can choose here F5 and I click OK. So it's now introduced into the field together with its coordinates. And now it's ready for me to click OK to do the interpolation. And let me come one page down and come to the region where it was affected. And we see that the F5 now, though still noisy, it has been, the extreme deflections have now been removed. So for that, let me overlap the previous node with the filters. And you can see here how the F5 was before and now how it's looking. But something important to remark is that now this channel F5 is not the real data that we recorded in the laboratory. It's rather an interpolation produced based on information from other channels. So this is no longer our original physiological recording, which means in some occasions we may need to be careful if we want to interpret data from this channel. But right now I'm doing this to facilitate subsequent pre-processing. And for the ERP components that we have an interest in, those are affecting more of the visual area and not the frontal area. So we can safely interpolate. All right, now that we have the interpolation, and we have already filtered our data, then we can think about the re-referencing of the data. But for that, let me get back into the slides. So to talk about re-referencing, first we need to remember a little bit EEG referencing, because as you surely are aware, the voltage in the EEG can only be recorded as the difference between two sides. And for that reason, we first need to have a ground electrode. And this ground electrode is connected to the amplifier's ground circuit and then subtracted from all the other channels. And this allows us already to record EEG, and we could leave it as that. However, having it in this scheme will introduce a lot of noise from the amplifier into the recording. So to reduce this noise, what is done during the recording then is to have a reference electrode for which we take one normal scalp channel. And once it's already referenced to the ground, and then this electrode, we will subtract it again from all other electrodes. And this will allow that the electrodes will, the other electrodes will better pick up electrical potentials at the different sides of the scalp. So what happens here is that when we subtract the reference from all other electrodes, all the noise that they had in common gets subtracted, and in this way we can get a cleaner EEG measurement. So in this way, differential amplifiers will amplify the difference in electrical potential between the reference and the scalp channels. But in this process, then the reference gets subtracted from itself, and therefore in our raw data or during our recording, it is zero. And that's that's the reason why we cannot see activity of the reference channel. But now we come into the re-referencing, and keeping in mind that the signal at each channel now reflects the difference in voltage to the reference. So for example, if we use the online reference FCZ, now all the channels are in reference to it, so FCZ gets subtracted from each one of those channels. But as a consequence of that, then the channels that are nearby FCZ, well, they would have very similar activity. So when the subtraction gets performed, then the activity of these channels gets largely reduced as well. And if we wanted to analyze data that is around this region, then this could be problematic. So for these reasons, we can resort to re-referencing, and this new reference that we want to use should pick up as little signal of interest as possible and the same noise as the scalp channels, and it should avoid hemispherical bias. Ideally, the reference should approximate a value of 0 to be neutral, and a good solution that is applied to achieve this is the average reference. So if we switch to the average reference, what happens is that from our original recording, now we make an average of all electrodes, and then we will reference each one of the electrodes to the average. So we will subtract the average from each one of the electrodes. And this includes the original online reference. So it would be 0 minus the average of all other electrodes, and will allow us to recover what we originally used at the as the reference as the negated new reference. And importantly for this average reference is that it works better with higher electrode counts and larger scalp coverage. So here we have, for example, with our recording 64, which makes it safe to use this referencing scheme. But there are other referencing schemes, as for example, the average mastoids or the earlobes, where instead of averaging all the electrodes, we will generate an average of electrodes located at the mastoid area or placed over the earlobes, and then do the referencing of each electrode to that average. But to look closely into that, let me show you what are the effects of re-referencing on data. And what will happen is that the evolution along the time, or the waveforms, will be different, because voltage values are expressed in relation to the new level of 0 voltage defined. And the effect of this, that we can see over here is in these diagrams, or in these plots. What we have is the plot of a P300 component obtained from an oddball paradigm, where our black waveform is the one for the frequent stimuli, the blue one for the rare stimuli, and then the red one is the difference wave. So black frequent, blue rare stimuli, and the difference of the two is the red one, where we would expect to see our P300. And when we have our online reference at FCZ, and we look into channel CZ, which is very nearby, then we can see the difference between the two conditions is rather small, because the reference is subtracting a lot of activity, and this reduces the sensitivity of the to the experimental effect. Then when we do re-referencing to the average, then we are including all electrodes across the scalp, which allows the difference to get bigger. So now there is more sensitivity to this effect. However, the average reference still has many electrodes that are nearby FCZ. So in the case of the mastoids, which are far away, we can see that the measurement becomes more sensitive to the difference between the two experimental conditions. So in this case, For example, it could be convenient to use a mastoid reference. Something else to consider is that while the waveform will change, the topography will be consistent. So the magnitude of the values will change, but the relationship of the topography between the different channels will remain consistent. You can find more information about re-referencing in our press release, choosing the reference and why it matters. But for now, I would like to show you these processes in Analyzer. And before we apply them to our main dataset, I would like to show you how this process looks when performed step by step. So what I did here is that I manually generated a reference channel. So if I open this node over here and you look into the top, so here I basically generated the average of all channels, where you can see the result over here. And this is our average reference. And then in the next step, I would subtract this reference from all the channels to re-reference the data. And I would also do 0 minus the reference to recover the recording, the online reference, which was FCZ. And if you notice, it is a mirror image of the reference that I estimated. So if I overlap with Analyzer's re-reference transformation, then you can observe that the results are the same. But let us look closely into the new reference, how it works. And for that, let me close this dataset and return to our main dataset to apply the new reference. So we can come here and select new reference. So at first we can select here which channels will form the new reference. And since right now I want to use the average reference, I will choose all channels and select. But be careful here, because in my selection right now there were the EOG channels, so I need to remove them. So BEOG, HEOG, and here this GSR channel was another skin conductance measurement that was performed. But not only are we not using this right now, but it's also a completely different type of measurement, so I will also remove it. And here we have the option to include the implicit reference into the calculation of the new reference. So that means to include our online reference into the new estimation. So I'm going into next. And here we select to which channels we apply this new reference. And again, I'm going to choose all of them. This time I will leave in the EOG channels, but I want to remove the GSR channel. And also use this option here that actually I'm going to unselect this option, sorry, because what this means is that all the channels that are on this box over here will no longer remain in the dataset after we finish the re-referencing. So now let me click on next. And here I have an option to add a suffix to the names of the channels after I finish the re-referencing, which can include the name of the reference that we use. But I wouldn't like to add a suffix right now, so I'm not going to include anything here. And here we get the option to reuse all reference channel as the negated new reference, which I'm going to select. And since our online reference was FCZ, then I type in here FCZ and now finish. So here we get our re-reference data. And if we pass the page here and one more, so in the end we also see now the inclusion of our FCZ channel. But let me come back to the first page, because now another characteristic of this average referencing is that it also helps to reduce noise slightly. And this reduction is now allowing me to see a pattern that was not entirely evident before. So if I call your attention into this TP9 channel, you may notice this regular bumping that sometimes looks like it was the EEG, but I want to make sure of that. So for that, I can generate a mapping like we've seen before. So mapping view, and I'll try to center. Okay, or let me come to the next one over here. And yeah, now we see more clearly that here this is having large activity on this lower left area, which is typical for the heartbeat or pulse artifact. So if I come to the next one over here, it's also showing the same pattern. And if I try it again in the next one, so let me try to center. So now we see again the same pattern. So there's a possibility that having this could interfere with my following measurements. So something I would like to do is to attenuate or remove the influence of this artifact. For that, I can use the ICA later on, the independent component analysis, which we can also use to reduce other artifacts like the blinks that we see here. These are very consistent artifacts that show consistently the same type of activity, and we can use ICA to reduce them. But before that, if you remember, in between the blocks, there were these very noisy periods. So this kind of noise can affect the results of the ICA because these are not the kind of stereotypical artifacts that we saw before. Instead, they are rather chaotic. So what we would like to do before doing ICA is to reject these kind of artifacts and others that may appear in between the data. So for that, let me come into raw data inspection. And here we have the options to do this inspection manually. So for example, with this, I would scroll all the way to this region and then manually drag the mouse to mark it as an artifact. Automatic or semi-automatic. So right now I will do the automatic. And in the next tab, we can select the channels where this transformation will be applied. And I'm going to enable all the channels, again, except the EOG channels, because if we leave the EOG channels in, then all the blinks and the eye movements that they register will be marked as an artifact. But what we want is to later remove these artifacts or attenuate them using ICA. So right now we only want to remove this larger noise. So here in the criteria, there's different criteria that can be used, but for this example, I'm going to disable them because I only want to use the amplitude criterion. For more information about the others, you can check also our webinar channels where we have a webinar on artifact handling especially. But right now, I'm going to use amplitude and I will enable it and leave these standards. So what this means is that whenever the data reaches a level of minus 200 microvolt or plus 200 microvolt, it will be labeled as an artifact. And because normally the artifact starts and ends beyond the threshold crossing, then we can also use this option to mark before the event 200 milliseconds and after the event 200 milliseconds. So now we have our criteria, we have the channels and automatic mode. So now I come into OK. So it will now search for the artifacts. And since this is automatic mode, now the outputs are there and it doesn't ask me to confirm. I ask it to do it automatically, but still I can see what it did. So if I jump now to the area of the breaks, you can see the artifacts have been marked with this reddish color. And down here, also you can see in the navigation bar the sections that have been marked as an artifact. But to verify, let's go through our block and see if it marked anything else as an artifact, which we can already see here. So this deflection over here on channel FP2, which coincides also with a blink, was removed. And same over here. It happens sometimes, but we can see that in most occasions it doesn't happen. So this is the trade-off now of the automatic manner that I use for the artifact rejection now. So with my current criteria, it removed some of the data in the analysis section because some of the blinks were large enough to reach the criterion. So we could modify this or use another rejection criteria. But right now, I would decide that I will take this trade-off because I know also that I have many trials that I can leave still for analysis. And when I want to replicate this processing later with other data sets, this automatic manner will be much faster. But now I would also like to highlight to you another aspect about the order, how we apply these steps. So now I apply the raw data inspection only after the filters have been implemented and before the subsequent independent component analysis that I want to do. But let me show you what would happen with this amplitude criterion if I did it before filtering. For that, I'm going to drag it and drop it here to change sampling rate. And it's going to search for artifacts. And I will activate the output. And you can see that now everything is marked as an artifact, because if you remember, if I deactivate the centering function here, the channels have very large offsets, so that means that the entire time they are above our artifact criterion. So everything is an artifact now. And for that reason, since I wanted to use this amplitude criterion, then I only did it after filtering. There are other criteria which are not just the amplitude that could be used instead. However, we cannot go deeper into that right now. And I would like to remind you can also check our artifacts webinar for that. But for now, just let me delete this node and continue into our raw data inspection. And now that we have removed these artifacts in between, we can resort to the independent component analysis to remove our other more stereotypical artifacts like the blink or the heartbeat artifact. But before we apply it, let's briefly check about independent component analysis in the slides. So for independent component analysis, we assume that there are different sources of brain activity, and each one of these sources has its own time course. Then when we record activity with the electrodes from the scalp, these electrodes will receive a mixture of the signals generated by these different sources. So something that can be done with ICA is to separate these sources, and we could either select one to continue working only with that source. So this would be put into the different components. So we would select one component to continue working with it. Or what we want to do in the following example is to select one or more of those components and remove it from the data and then reconstruct the data without that component, which would reduce the influence of that pattern in our data. And in our case, that pattern is the blinks, the heartbeat, pulse, and the eye movements. So as you can see here, now the influence from this blue region is no longer reaching the channels. So ICA is a blind source separation algorithm, which is purely data-driven, and ICA components are based on statistical properties of the signal and do not map precisely on physiological processes. And further, ICA is a complete decomposition method where the number of maximum signals that can be extracted is limited by the number of sensors that we have available. So let's come now back into Analyzer to implement the independent component analysis, where we can find it over here. So I'm going to click here in ICA, and there are different options which we cannot review right now. And again, this is available in our webinar channel with a deeper explanation. But let's include all our channels into it, including also now the EOG channels. And here we have the option to either run the ICA across the entire dataset or an interval. For example, if I choose whole data, then the ICA will run and will sample to separate components from the entire recording, which would take a longer time. But it's also the reason why we wanted to remove the artifacts in between the blocks. But then another option that would speed the processing is to use an interval. And for example, if I know that I want to remove blinks and the heartbeat, the pulse artifact, and the eye movements, I also know that I have all three of them in the first block of data. So I could use an interval and run the ICA on that segment of data to sample from those artifacts and be able to separate them into components and then remove them. And this would be faster than the entire data set. So right now, I would opt for that option. So I will click on next now. And here we have different options for the ICA algorithm, which I'm not going to modify. But here on top, these options for sphering. So now for removing components that reflect artifacts, we are going to use this classic PCA. And we will come back to this in a moment. But what this is doing is to check for the linear dependency between channels. So let me click on finish. And now it computed now this sphering that we just saw. And because of that, now it's triggering this warning for us. But it's telling us that you want to compute a number of 66 ICA components, but the data has only rank 64. Do you want to compute only 64 ICA components instead? So what this means is that as the sphering is checking if there is dependency between the channels, it finds that there is indeed, or channels are indeed dependent on each other to a degree. And this is something that I introduced with two previous pre-processing steps. So if you remember, we have the topographic interpolation, where we generated a new channel based on information from other channels. So that one channel then, as I was mentioning before, is not our original recording. Rather, it depends on the other channels. Therefore, this is detected by the sphering. And later on, we did the average reference, which, if you remember, is the average of all channels, then gets subtracted from each channel. So in a way that also increases the dependency between the channels. And because of that, we can calculate fewer components than the channels that we have available. And this is what this is warning us about. But this is not problematic. The most recommended action would be to accept the reduction. So do you want to compute only 64 ICA components instead? So it would be recommended to click yes to have a more accurate decomposition. If we click on no, then we would get still the 66 components, but we would risk inaccuracies. So unless you have very well fundamented reasons for going for 66 components or the not reducing the rank, then the recommendation would be to click yes, which I would do right now. However, since it has been already calculated in the copy dataset, I'm going to click cancel to come back into the results. So let me expand all. So we have here a branch with our original ICA and then the inverse ICA. And here we have a separate branch where I did ICA without interpolation that I will show you later. But for now, let me double click here on the ICA, where we can see the output, which is now no longer EEG channels, but rather the components that were obtained from them. And then some of these components I removed to reconstruct the data without them, and that was done here in inverse ICA. So I would like to show you what I did here, and for that I'm going to right click and come into edit parameters copy, which would allow me to modify some of the parameters I use here and then generate a new branch over here with these new parameters. However, I'm not going to modify anything. What I want to do now is to show you what was done at this step. And what we see now is the components just as before, so just with a different scale. So let me adjust the scale for them to look like before, which now we can see here. But we also see over here listing of all the components and the topography of these components. So for example, here we can see component 0 shows a typical topography of the blinks. So I marked it for removal as red. And then component 1 is showing us the typical topography for lateral eye movements. So I also mark it for removing it. And then there is other components over here, which are not artifacts, so I didn't remove, all the way until this component over here, 43, which, if you remember the maps from the pulse artifact that we saw before, they look like this. So this is showing us that this component reflects the heartbeat artifact that we saw before. So to confirm that, let me go one page down. And if we look here, component 43, it's looking like the heartbeat that we saw before that has been isolated within this component. So after choosing these 3 components for removal, then I would click finish, but right now I'm going to cancel because this has been already implemented. Okay. And now here in this node with inverse ICA, what I get is the data with the correction that reduces the influence of the blinks, the heartbeat pulse artifact, and the lateral eye movements. So for that, let me overlap the previous node before we did the ICA correction. And we can already see here the reduction of noise. If we look into the TP9, then you can see also the heartbeat, which was very noticeable there, has been reduced. And also the influence of the blinks has been largely reduced. And okay, so at this point, oh yeah, beforehand, sorry, let me show you our ICA without the interpolation. So in this case, I skipped the topographic interpolation step, but then I applied the rest. And if I come into inverse ICA and into copy, then we can see that, okay, then let me adjust the scale. Then we can see that the we still get our components, but then there are many components that are showing a pattern over here, because if you remember, we have the noisy F5 over there. So this causes to occupy space from many components as they go through trying to separate the patterns in the data. And the effect that this can have is that since they are occupying many components, then the decomposition of other components may be less precise. And when we want to remove artifacts, it may be possible that they also include some EEG activity in them, so that when we remove, for example, a blink, could be that some EEG activity was in the blink component, and then when we remove it, we risk reducing our EEG activity as well. So it didn't happen in this case, but it's something that could certainly happen. So I'm going to cancel. Okay, now. So now to continue, just let me remove this branch over here so that we can continue our analysis in here. And now that we have the inverse ICA, we already use the EOG channels that help us in removing or reducing the influence of eye movements and blinks. So since we don't want to submit those channels to further processing or transformations, then we can remove them from our data set, for which I can come here into Edit Channels. And if I scroll all the way down, then I will see these channels, which I can just unselect and click OK. And then if I increase the channel count, then we will see that the EOG channels are no longer there. And now that we have cleaned our data and re-referenced our data, filtered, then we can now perform the segmentation around the presentation of the positive emotional pictures. So for that, I can come into the segmentation transformation, and I can use this option over here, create new segments based on the marker position. Next, then I will select my positive stimuli. Next, and here I can select the timing around the stimuli, which is going to be from -200 that we can use for baseline, up to 1000 milliseconds for the analysis. And here we have options to allow overlap segments, which we don't need right now because our segments are not overlapping. And also to skip any interval that has an artifact on it already. However, I would like to have all of my 180 trials in the segmentation, so I'm not going to use this option. And I click on Finish. So we get now our segmentation, and we could rename the segmentation here with a right click and then rename. And I'm going to call it segmentation positive. So in the case later on, for example, if we wanted to have the negative and the neutral, then we can rename them in the same way. And now we see our trials with a little bit of a different view. Now we have each one of the channels in a box, and we see for the entire trial, where at level 0, we see the presentation of our stimulus positive, -200 for the baseline, and then the period afterwards. And then we can see also what has been marked with artifacts before is here, which is only being displayed for information, but it's not going to be considered later on for analysis. Okay, so then we can apply further processing into this segmented data, but it's a moment where we can approach the topic of the order of processing steps. And for this, I would like to get back into the presentation. So you may have noticed that the order may vary in different studies, or that you can apply them in different sequence. And something to consider at first is that there is no best method or best sequence, which depends actually the sequence very much on the prerequisites that you need for specific analysis steps. For example, filtering or raw data inspection may be helpful to prepare the data for other correction methods, while some algorithms like the ICA or others like ocular correction require the data to be already denoised, which is the process that we implemented right now. So first filtering and raw data inspection, followed by the ICA. The sequence also depends on the research goal. So for example, it depends on the desired outcome measure, and the sequence may be modified according to this aim. Or you may also want to replicate a previous study exactly as it has been implemented in a paper. The sequence also depends on the data characteristics. So for example, noisy datasets might require a more thorough processing and artifact rejection. So some processing sequences are interchangeable. So processing steps that apply linear operations like average or subtraction lead to the same result irrespective of the sequence. As you may see here, for example, baseline correction, average, and pooling. If we switch the orders, for example, applying pooling first, followed by baseline, and finally average, or average, pooling, baseline, this would produce the same output because all of these are linear transformations. For other processing steps, the sequence matter. So for example, applying artifact rejection based on absolute amplitudes to data that is baseline corrected or not baseline corrected. So in this case, what we see is that the data with the baseline correction is shifted upwards. And if we are using an absolute threshold of 80 microvolts, then the baseline corrected data reaches the threshold and it would be marked as an artifact, but the non-corrected data does not reach it. So we have different results in this case with these two different orders. And other case that might happen is, for example, if you have together with the average, you have standard deviation, then the standard deviation may change with the different orders, because the standard deviation is also nonlinear transformation. Okay, but to demonstrate what is linear and nonlinear, because I am mentioning it a lot, I would like to use one kind of operation as an example, which is the moving average. So what a moving average does is that from a series of numbers, it takes a window, and within that window, it will calculate the average of the numbers. Then it will move by one step and calculate the average again, and so on until it generates an entire new number series made of averages of the previous number series. So now we can use this operation on sine waves to exemplify linear processing steps. So linear processing would need to satisfy two conditions. So in condition one, we can see that processing signals and summing the outputs is equal to summing the signals first and processing the outputs. So applying the moving average, in the case of these two sine waves, we can first do the moving average, and then from the results that come, make a summation and get this result over here. Or otherwise, we can first sum the two sine waves and then use moving average on the result and get the same final result. For condition 2, we can have a signal and we can scale it first and then process the output, or otherwise we can apply the processing and then scale the output, and the result will be the same. So again, with moving average, we have this sine wave over here. Then we can first scale it, for example, multiplying it times 2, and then use moving average. Or otherwise, we can use first moving average and then scale it, and the result will be the same. Now, a process that does not satisfy any of the two previous conditions will be nonlinear. So, for example, if we take artifact rejection with a threshold of 9 microvolts applied to these sine waves, then with the first example, we can first do the artifact rejection and we get our artifacts over there, and then we can scale the sine wave. But on the other way, if we first scale it and then we do artifact rejection, you can already observe how we get different results because the point of threshold crossing is different after we scaled the sine wave first. But normally, when we, as we go through the EEG preprocessing, we wouldn't be performing this kind of test. So to help us distinguish between the linear and nonlinear processes, we can use these following rules, in which linear processing steps can involve summation and subtraction across data points, or scaling through multiplication or division. But linear processing excludes processes like operations that combine scale values in other ways than summation or subtraction, the definition of scaling factors that are based on observed data values, or the detection of predefined threshold values, as we just saw with our artifact rejection example. But now, to bring further examples on EEG, then we have here 3 trials on one channel. So one trial, the second and the third, and we're going to apply baseline correction. So what the baseline correction does is that it will sum all the points from the trial baseline, and then it will divide the result by the number of points, so obtaining the average of the baseline period at each trial, and then this average will be subtracted from the waveform to obtain the baseline corrected data. And when we check these processes, then we can see that baseline correction is linear, as it only involves the summation and then dividing by the number of points and subtracting. As another example, we can see here the ocular correction from the Gratton and Coles method, where what happens is that first it locates the blinks and estimates a correction factor called K around the blinks. And once having it, it will perform a subtraction of EEG minus K times EOG. And this produces the result where the influence of the blinks over the EEG will be reduced. But as you can see, this process is nonlinear because it involves the scaling of a factor or a scaling factor derived from observed data values. In this case, this K correction factor. Well, all right, now I would like to come back to Analyzer to apply some more processing steps. Now that we have our segmentation, then we can start, for example, with our nonlinear artifact rejection. So we rejected some artifacts before, but now I would like to use a stricter criterion to remove residual artifacts that have not been corrected or removed so far. So I'm going to use the semi-automatic mode. I'm going to enable all channels, which at this point are only the EEG channels. And in the criteria, again, I'm going to use amplitude only. Oops. Unselect and unselect, unselect, then amplitude. But now I am going to use a criterion of minus 100 to 100 microvolt. And we're going to, so we have the criteria semi-automatic, yes. So now we click OK. And since we are in semi-automatic mode, Now it's going to show us the output for us to confirm or reject or modify. And for that, now this is one trial and it's showing us all the channels. And here we have a table with all the artifacts. So I'm going to jump to the first one, which is in the next page. So for that, I'm going to increase the channel display. And we can see here, this channel is showing a drift that is reaching our threshold for artifacts. But to visualize it in another way, I can right click and come to switch view, grid view. And now we see that this channel TP8 is really showing an artifact. If I come into the next one, then I see that this region has been also marked as an artifact, but it's not looking particularly noisy. But then if you remember that we have this centering function and I deactivate it, I notice that this area has residual offset. So because our criterion for artifacts was at a certain level, it's surpassing that level, even though the data, it doesn't look that noisy. And the reason for that also is that I haven't yet performed baseline correction. So because of this offset, then this trial is being marked as an artifact. But on the other side, if I come here to the end and I show you this artifact, so this one in turn is a very clear artifact that would contaminate my baseline. So the reason to do artifact rejection before the baseline is that I want to prevent this kind of bumps to enter and contaminate the baseline for the rest of the trial. So after doing this, then I'm going to click OK. And now after artifact rejection, I can come to the baseline correction. It's already shown us the minus 200 from to 0 for baseline. So I click OK. And if I overlap, then I can see how the offset has been reduced by the baseline correction. But now, talking about order of steps, then I can try the opposite order. So first apply the baseline correction. And I activate the node, and then I will come into artifact rejection, and it still remembers the criteria that I used before, so the amplitude and all the channels. So I'm just going to click OK. So now we first baseline corrected, and then we are applying the artifact rejection. And I'm just going to click OK for now, because to highlight the differences, I would like to bring your attention to this lower part over here. And I'm going to switch in between the two orders that I just used. So artifact rejection second and baseline correction second. So just look here at these red markings, which is where the artifacts are. And as I switch between the two, you may notice how there is a different selection of artifacts between the two. Which order to use? Again, it depends on what you need and your criterion. So here what I wanted to do was to prevent large artifacts from entering the baseline, but that came at the cost that some trials that still had some offset were marked as an artifact. However, I'm going to come with this to continue with this order. So I'm going to erase this other branch over here from the baseline correction. And then something else that we can do is to generate the average. And I click OK. And if I adjust here the amplitude, then you can see we are obtaining our ERP form. So we can rename, right click and rename, and we would call it average positive. So something else that we can do is to generate a pool of electrodes that may reflect, for example, an area of interest over the scalp. And for that, we come into channel preprocessing and then pooling. And then we select that we want to keep all channels. We want 2 pools fresh. And then, for example, if I wanted to make 1 pool on the left, I will just choose, for this example, C1, C3, and then 1 on the right, C2, C4. And here we can rename them. So I will call it here left, and this one over here right. And then I'm going to click OK. So if I come until the end, then I see here our pooling that we got. But to remember about the linear steps, because these steps that we applied right now are all linear, then here we can see them applied in different order. And if I come into pooling and then I overlap the others, then the result is the same. And also if I come down to the pooling over here, then I can see the result is the same. All right. So now that we have completed our ERPs, I would finally just like to highlight some of the adaptations that can be done for other kinds of analysis. So we checked our overall EEG preprocessing and then wait for ERPs, and now some adjustment for others, which are some pitfalls that we need to consider. For example, with the fast frequency transform, it operates optimally if it's using the sampling rate is a power of 2. So if we don't have a power of 2, we can downsample, for example, from 1000 to 512 or 256 Hertz. For time frequency analysis, then by the very nature of this kind of analysis, then we have border effects when it encounters the edges of the trial, and smearing effects that displace slightly our results or prolong them over time. So something that we can do to deal with this is that we need to have a longer baseline that leaves a safety margin that avoids these effects. Or others like connectivity analysis. So if the channels are referenced to the common average reference like we use right now, the signals might indicate a false synchrony. So we need to have the caution of making sure not to use the common average for this kind of analysis. So I would like to show you this here below, where we have our original processing, and then here we have different branches. Here is one for wavelet analysis, connectivity analysis, and frequency analysis, which I would show you now. So here we perform analysis for the eyes closed condition, for which we change the sampling rate to 256 Hertz. Then, which is a power of 2, of course, for the FFT. Then the data was segmented for the entire eyes closed block. Then this data was segmented again, now into consequent 2-second periods. And for each one of them, the fast Fourier transform was performed, which we obtained here. And then finally, all the trials were averaged to obtain our final result, which is showing us the classical alpha activity when closing the eyes. Then I would like to show you here our branch for the wavelet, where you can observe we obtained longer baseline, which has already since the experimental design. And this baseline will allow us to follow the recommendations for wavelet analysis. So first, then we obtain here our ERP, which is as before, but with a longer baseline. And finally, for the wavelet analysis, let me reprocess it. Here we defined the parameters for the wavelet analysis, which we cannot go through right now. But what I would like to call your attention to is here that we use the normalization. And for this normalization is where we require a reference interval, which, if you see here, runs in a period that avoids coming to the edges of the trial to prevent effects of this smearing and border effects. And finally, for connectivity, as I mentioned before, here we have our, this transformation called CSD for current source density, which is commonly used in this kind of analysis. And since we previously had the average reference, then we apply it here as well to not do connectivity analysis with the average reference. But importantly also, we applied it after artifact rejection, because if you notice, the data now looks very different to what it was looking before. So we first reject artifacts, then do the current source density, and then we apply wavelets. From the wavelets, we manually used a data cache. So this data cache will store again the data in the hard drive so that it can be more easily, the next transformation can be more easily computed. So we come here finally into the coherence analysis for connectivity, which we cannot interpret right now. But importantly here is that before that, we use the data cache, because this analysis is very demanding, and it's better to have the data already stored in the hard drive. Okay. Some concluding remarks after checking these processing pipelines is that you can always check publications from your field as a good starting point to start processing your data. So checking how other researchers have done it, or if there's any guideline. Once you decide, apply the same pre-processing for all participants and try not to vary. Exceptions can be, for example, if you decide to interpolate different channels for different subjects according to your need. Then also check the effects of the pre-processing after you apply it. So, for example, check how many trials you have left, that you have not missed many trials after you, for example, reject artifacts. Because also that it's important you have sufficient trials for the average, and that the number of trials do not differ between conditions. Then always visually inspect all individual raw data sets, and after crucial pre-processing steps, especially like the ocular correction ICA, which if we, for example, remove too many components, it may come to create some distortions in the data. So we can visually confirm that this is not the case. And only compare waveforms with the same reference. So with this, I would like to thank you for your attention, and we come to our section on questions.
Thank you very much, Fernando, for this nice presentation. We are running a bit over time. Sorry about that. So I'm now quickly passing over some questions to you, and please proceed once you receive them. Thank you, Fernando.
Yes. All right. So I'm getting here some of the questions. So one of them, my ERP waveform looks very noisy and want to smooth it. Can I apply filters on the grand average waveform? Then I would say you can apply them for display, but preferably not for the analysis of your data. So it would be preferable if you try to apply or try to modify your pre-processing beforehand to see if you can reduce the amount of noise. Or if you just apply it for the display, then mention in the plot that this waveform has been filtered for the display. But definitely for the analysis, then wouldn't use the filter data of the average grand average. Then let me see further questions. Do we include the interpolated electrodes in the new reference? So yes, this is something that you can do, especially if you saw that the channel beforehand was largely noisy and it would introduce a lot of noise into your new reference, then you can interpolate it beforehand. Okay. Yeah, okay. Then another question is, could we please know what does order 4 mean in the filtering? Thanks in advance. So the filter orders is reflecting us the filter response, or how the filter is attenuating the different frequencies. So for example, the order 4 will produce an attenuation of 24 decibels per octave. So that means it will reduce the frequencies by 24 decibels by every octave, which is like the doubling of the frequencies. And then filters of 2 and 8, respectively, they would do a 12 decibel per octave reduction, and then 8, 48 decibel. In this case, I use the number 4 since it's a good trade-off that can reduce, for example, the high frequencies sufficiently and the low frequencies with low risk of producing distortions in the data. Then another question that we have over here. Okay, this question is related to the previous. What does changing the order from 2 to 4 to 8 does exactly? So I believe this question has been addressed already with the previous one. And all right. So maybe one more. Which states my reviewer has asked me to change the reference, but I do not want to repeat the analysis. Can I re-reference at the latest steps? Then yes, you could do this re-referencing, but only, I would say, to get an idea of what your output would be. However, the best recommendation, I think, would be if you reprocess and repeat the new reference at the same point where you had your original referencing scheme, especially because if you later have other processing steps, or how to say this, that yeah, if you have especially non-linear steps afterwards, then I would say it's better that you keep the original, the referencing at the same original point. Because now, yeah, we got one more question over here, which says that exists any way to reject and interpolate bad channels automatically in Analyzer? No, at the moment we do not have this option available. However, you could inspect your data visually. You can, for example, increase the channel count and use options like the ones I was using on screen, where you can highlight a channel and see the evolution over time, which facilitates detecting these noisy channels. All right. So after these questions, I would like to recommend some further reading from our materials. from our press release, Choosing Your Reference and Why It Matters. Also our press release on independent component analysis, and the Brain Products webinar channels, where you can find deeper explanations of the different transformations and procedures that we observe. So, for example, the webinar on EEG artifacts types and handling strategies, spectral component and analysis. There's a series of with various webinars about this, and likewise for EEG fMRI series of webinars. And there's also further reading that you can do. For example, the book from Stephen Locke, An Introduction to Event-Related Potential Technique, or from our current presentation, here you can find about the Gratton and Coles ocular correction, guidelines for reporting on electroencephalography studies, and deeper information about ICA. And if you are interested in the Nenki affective picture system, you can check also these references over here. So thank you very much for your participation and attention. You will receive a follow-up email with a link to the video recording of the webinar. And you can always visit our Brain Products webinar channel, where you can rewatch this and past webinars. If you have any further questions about the content of this webinar or other topics around Analyzer, please feel free to contact us at support@brainproducts.com. And with that, I would like to wish you a very nice rest of the day. Thank you for your attention and happy pre-processing. Goodbye.